Hello there, and in this video we're going to continue our discussion of improper integrals. Let us first discuss the different types that we have discussed so far. The first type of improper integrals are ones of the form the integral from a to infinity, the integral from minus infinity to a, and the integral from minus infinity to infinity. And here a is some finite number of f of x dx. And here, f is finite on the interval of interest. So namely, it's finite on a to infinity, minus infinity to a, and minus infinity to infinity. The second type of integral, or improper integral, is ones of the form the integral from a to b of f of x dx with f of a or and f of b is equal to plus or minus infinity and finite on the open interval ab. So type 3, which we'll discuss primarily in this video, is the integral from a to b of f of x dx with f discontinuous on I. And when I say discontinuous, I'm going to be focusing primarily on infinite discontinuities. Removable discontinuities and jump discontinuities actually do not pose much of an issue. Yes, the fundamental theorem cannot be directly applied to these types of integrals. For example, if you have a jump discontinuity and you want the integral on some region that includes that, you can simply just find the integral from the left endpoint to the jump discontinuity and then find the integral from the jump discontinuity to the point, and you can get it. Same thing goes for the removable discontinuity. So if you want to integrate over that region, you can just integrate up to that point, and past that point the removable discontinuity actually does not pose any issues. But the issues typically occur when you have an infinite discontinuity. So let us assume we want to integrate over, say, this region. So namely, what is this area plus that area equal to? And this is what type 3 primarily focuses on. All right, so let us look at the discontinuity cases in a little bit more detail. So let us assume that f of x is equal to the piecewise function x squared for x less than 1, x plus 1 for x greater than 1. So let us assume we're interested in the integral from -2 to 3 of f of x dx. So the first thing to observe is that this integral is -2 to 3, and this possibly has a jump discontinuity at x is equal to 1. So what we need to do is integrate this function f of x over the interval -2 to 1, and then add to it the integral from 1 to 3 of f of x dx. We cannot apply fundamental theorem of calculus to this first piece, but the fundamental theorem of calculus applies to the first and second integral because f is continuous on the interval -2 to 1, and it is continuous on the interval 1 to 3. So from here we can say this is the integral from -2 to 1 of f of x. So f of x on this interval is going to be all values less than 1, which is going to be x squared dx, plus the integral from 1 to 3, and f of x is defined to be x plus 1 on that interval as well. So by the fundamental theorem of calculus, we know that this is going to be equal to 1/3 x cubed as x goes to 1 and then x goes to -2, plus the antiderivative of x plus 1 is going to be 1/2 x squared plus x, evaluated at x goes to 3, and as x goes to 1. So plugging in everything, we have this is 1/3 times 1 cubed minus -2 cubed plus 1/2 times 3 squared minus 1 squared plus 3 minus 1. So that's going to be equal to what? So we have 1/3 times, so 1 negative 2 cubed is -8, negating that becomes a positive 8. And then we have plus 1/2 times 9 minus 1 is going to be 8. And then 3 minus 1 is going to be 2. So we have 8 plus 1 is 9 divided by 3 is 3, plus half of 8 is going to be 4, plus 2, so that's going to be 5 plus 4, which is equal to 9. All right, so jump to discontinuities, and similar for removable discontinuities, as I mentioned before, are not that big of a deal. So let us state an extremely important definition that is often used and misinterpreted in the literature, and that is this. So let us assume that the integral from a to b of f is improper, and the integral from a to c, or the integral from c to b, diverges for some c in the interval ab, then we say that the integral from a to b of f also diverges. So this is a definition that a lot of people sometimes twist around based on whatever interpretations. So now let us introduce a definition that is sometimes used to avoid this ambiguity and misunderstanding of this concept. So definition. So if the limit definition of a divergent improper integral and it could be convergent or divergent, actually. So a convergent or divergent improper integral exists. We call that value the principal value of the integral. So let us do an example. So this example is going to consider the integral from -3 to 2 of 1 over x dx. So notice that this function has a infinite discontinuity as x is equal to 0. So we need to sort of bounce around this singularity. So we can rewrite this as the integral from -3 to 2 of 1 over x dx plus, the integral from 3 to 0, So the integral 3 to 0 plus the integral from 0 to 2 of 1 over x dx. So one can find, so if we do the limits as, let's do m goes to 0. So we can do this to be the integral of -3 to m of 1 over x dx plus the integral of m to 2 of 1 over x dx. So this is going to be equal to the limits as m goes to 0. So that's going to be equal to the natural log of m minus the natural log of the absolute value of -3 plus the natural log of 2 minus the natural log of m. So if we look at just these independent limits, we can find that this is going to be equal to -infinity minus the natural log of 3, and this is going to be the natural log of 2 minus -infinity. So if that is the case, we know that this integral diverges, and this integral diverges as well. So by definition, the original integral also diverges, right? But we need to notice something, because notice we have a -infinity and a positive infinity here. So do these infinities cancel? So if we look at the limit definition directly, so this is going to be equal to the limit as capital M goes to 0 of, so the natural log of m minus the natural log of 3 plus the natural log of 2 minus the natural log of m. Now if m is a non-zero number, which we can assume to be, we can approach this 0 from the right, then the natural log of m and negative natural log of m will cancel. And this is now going to be independent of m. So this is going to be equal to the natural log of 2 minus the natural log of 3, which is just going to be equal to the natural log of 2/3, which is a very pretty number. So from this, what can we say? So from this, we can say the integral from minus 3 to 2 of 1 over x dx diverges, but has a principal value. And some people will refer to it as a Cauchy principal value. Has a Cauchy principal value of natural log of 2/3. And we write this statement as the principal value of the integral from minus 3 to 2 of 1 over x dx is equal to the natural log of 2/3. So let's look at another example. So example 2. So what is the integral from minus pi over 2 to pi over 2 of tangent of x dx? Alright, so the first thing to observe is that tangent of x, recall, looks like this. And we have vertical asymptotes at plus or minus pi over 2. So therefore, this value is infinite on both of them. So if we split this integral up on two separate intervals, minus pi over 2 to 0 and 0 to pi over 2, which we can do. So we can rewrite this as the integral from minus pi over 2 to 0 of tangent of x plus the integral from 0 to positive pi over 2 of tangent of x dx. One can find that, well, what are these integrals equal to? So what is the integral of tangent? So we can find that that is going to be equal to the negative natural log of the absolute value of cosine of x, evaluated as x goes to 0, as x goes to negative pi over 2, and then plus the negative natural log of cosine of x, evaluated as x goes to pi over 2, and as x goes to 0. So we can't really approach pi over 2 and negative pi over 2, so we have to get extremely, extremely close to it, say from the right or the left. So as x goes to 0, cosine of x goes to 1, and natural log of 1 goes to 0, so that's no big deal. So this goes to, say, 0 minus, so when we plug in negative pi over 2, well, what is that going to be equal to? So that's cosine of negative pi over 2 is going to be 0, and natural log of 0 is going to be infinity, or negative infinity if you may. So that's infinite. So that means this integral diverges, this integral here. And you can find the similar logic because the antiderivative is the same, that this diverges as well. So one or both of these integrals diverge, hence the original integral diverges. All right, so how can we sort of bypass this in order to find the principal value of the integral? How can we address this issue? So let us return to the original integral that we have, namely the integral from negative pi over 2 to pi over 2 of tangent of x dx. So we've already established that this integral diverges. But it's possible that these negative infinities and positive infinities will cancel each other out. So it's possible that this integral does have a principal value. So let's see if we can find it. So we've already determined that it has singularities at both of the endpoints. So we can rewrite this improper integral via the limit definition. So the limit as epsilon goes to 0 of the integral of negative pi over 2 plus epsilon to pi over 2 minus epsilon. of tangent of x dx. So that's the limit definition of this improper integral. So again, we already know the antiderivative of tangent. That's going to be equal to the negative natural log of cosine of x. And we need to evaluate this. Where's my limits? So limits, epsilon goes to 0. So as x goes to positive pi over 2 minus epsilon, and as x goes to pi over 2 plus epsilon. So I'm going to plug in and subtract. So it's going to be equal to the limit as epsilon goes to 0. And I'll put a negative sign outside just in case I forget it. It's going to be upper limit, so the natural log of the cosine of pi over 2 minus epsilon minus the negative, the absolute value of cosine of pi over 2 plus epsilon. All right, so how are we going to deal with this? All right, so notice that this is a difference identity for cosine, and this is a sum identity for cosine. So remember the identity for cosine. So cosine of alpha plus or minus beta is going to be cosine of alpha cosine beta minus plus sine alpha sine beta. So I'm going to apply that to this and this using the appropriate signs. All right, so that's going to be equal to what? So that's going to be equal to the negative limit as epsilon goes to 0 of the natural log of, so we have cosine pi over 2 cosine epsilon. So that's minus, so I'm going to change it to a plus. So plus sine pi over 2 sine epsilon. Minus the negative, or minus the natural log of, so we're going to do the sum identity now. So the cosine of pi over 2 cosine epsilon, change the sign to minus sine pi over 2 sine epsilon. Wonderful. Now let us simplify these things as much as we can. So let's go to our unit circle for reference. So we're looking at pi over 2, so we're up here. So remember, that's the point 0, 1. Cosine is x, sine is y. So cosine of pi over 2 is going to be equal to 0. So that's 0, so that forces that term to disappear. That also forces that term to disappear. Sine is equal to 1, so that goes to 1, that goes to 0, that goes to 0, this goes to 1. So what do we get? So this is going to be equal to negative limit as epsilon goes to 0, so let's simplify, of the natural log. So what am I left with inside of this first one? This is going to be the natural log of the sine of epsilon. And remember that there's an absolute value bar inside this logarithm. And then we have minus the natural log of, and I have negative sine epsilon here. So the absolute value of minus sine epsilon there. So we can take the absolute value of the negative sign to become a positive sign. So this is equal to the negative limit as epsilon goes to 0 of the natural log of the absolute value of sine epsilon minus the natural log of the absolute value of sine epsilon. But those are the same exact natural logarithms, so both of them will cancel with each other, and we just have this is equal to 0. So what exactly does that mean? So if we sort of look at tangent, so tangent has this odd symmetric behavior. So if we look at the integral, say from 0 to pi over 2, and the other side, negative pi over 2 to 0, so we're pretty much saying that this yellow area and this blue area are the same, just on opposite sides of the x-axis. So even though they are symmetrically equal, they have opposite signs, so when you add them, they sort of cancel each other out. Even though they are actually infinite quantities. But even though they are infinite quantities, they are in a sense the same size of infinity, right? So what can we say in conclusion? Therefore, the integral from minus pi over 2 to pi over 2 of tangent of x dx diverges, for sure, because we can integrate from minus pi over 2 to 0 and get a divergent integral. So by definition, this integral diverges. But the principal value of this integral is equal to 0. And that's just some basic discussions on the principal values of integrals. And it's very important that you use the precise definitions of the improper integrals. That is, you have to use the same exact limit definitions. Because if you don't use those same exact definitions, you can actually get other values, which are actually not the principal value, but they can be something else. And that's not what we call the principal value. The principal value is based on the original definitions of the improper integrals. And also keep in mind that just because the integral diverges does not necessarily mean that the integral does not have a principal value. In most cases, they do, but in some other cases, they don't.